Yes. Good morning, sir.
Good morning.
Good morning. Uh,
Good morning, sir.
Good morning.
Good
so,
morning, sir.
Sir, good morning.
Good morning.
so I think, sir, we can start
Yes,
the.
yes. Start.
Okay. Okay. Thank you. Thank you, sir. So let me begin that introducing myself. I am Dr. Taposh Ghosh, Assistant Professor of Department of Applied Sciences, MAKAUT, West Bengal, and convener of this faculty development program, the online 5-day FDP on computational techniques in chemistry and material science, how to use the contemporary software tools. Now, on behalf of the organizing committee of this FDP, a very warm welcome to all the esteemed panelists and participants in day one of the 5-day FDP. Now, I'm very thankful to all the attendees who has joined so far and registered for the FDP and for their precious time to join the inaugural session as well. So today, barely there will be any scientific community or fraternity where computation did not play a pivotal role in their growth or in terms of their research activities. Let it be the industrial process or application in medicinal or in software industry, wherever we go. And we are lucky that our Honorable Vice Chancellor, sir, has foreseen that the field of education will not be an exception, and he has inspired and convinced us to emphasize on the computational applications while designing our in-house UG and PG programs, especially like MSc in applied chemistry and also in MTech in material science and technology. So he has always been guiding us and inspiring us to thirst into that field of computational chemistry. So I truly believe that for all of us, it will be highly benefited 5-day uh, program of development program for the faculties as well as the students and research scholars, and a lot of knowledges to take away at the end. So before we proceed, let me introduce or take the opportunity to introduce the today's panel members in the inaugural session. Today we have with us our Honorable Vice Chancellor, Sir, Professor Dr. Shoykot Moitro. We were expecting the Honorable Vice Chancellor of Islamic University of Science and Technology, Jammu and Kashmir as well, who are our organizing partner for this FDP. However, due to the busy schedule and some important meetings, the preoccupied meetings, he will not be able to with us, and but he has been generous enough to send his best wishes for the success of our FDP. And we have with us Professor Dr. Shukhendu Somazdar, Director of School of Natural and Applied Sciences. We have with us Dr. Radha Vallabh Bhor, Head of the Department of Applied Sciences. Dr. Arijit Bagh, Associate Professor, Department of Applied Sciences. Mr. Kalipada Dash from Department of Material Science and Technology, Dr. Anirban Roy from Department of Material Science and Technology, Dr. Mona Lisa Char from Department of Material Science and Technology, and of course our distinguished speakers of day one, Dr. Achinta Kumar Dotto from IIT Bombay. And we are expecting soon that Dr. Sumanta Bhattacharya from NIT Sikkim will join us soon. And so with this brief introduction of the panelists, and may I now request our Honorable Vice Chancellor, sir, to inaugurate the session and deliver his keynote inaugural speech. Sir,
Thank
please.
you, Dr. Taposh Ghosh. It's great that the Department of Applied Science, under the leadership of Professor Shukhendu Somazdar, and with the active participations of all the faculty members, have taken this endeavor for organizing these faculty development programs in one of the very interesting subject. Um, uh, I would like to take a liberty to say a few words, or express my opinions about these subjects, because I had some little understanding of chemistry, and I have some interest in this subject also. This area, particularly this computational chemistry, it's not a new thing. If you look at the historical perspective, it is almost 100 years old subject, because in 1929, when this quantum mechanics that emerged, that Paul Dirac he first made his famous statement that in principle, the physical laws necessary to understand all of chemistry were at that point known. The only difficulty was that their application to chemical systems generally led to equations that were difficult to solve. So that time, quantum principles could be applied rigorously only to very, very simple atoms or molecules like uh, uh, atomic hydrogen, atomic helium, or H2 plus, something like this. But in 1930, the first approximate quantum mechanical methods for molecules were developed, and that that resulted in some success in modeling electronic behavior in multi-electronic systems. That, for example, that time that Eric Huckel, he developed a rudimentary molecular orbital model for behavior of electrons in organic polymers. In 30s and 40s, that time electronic digital computers are developed, and this was after World War II, when these applications of computers significantly expanded. The application of classical and quantum mechanical principles too also proliferated and developed further. And that time, this computer technology that when it developed to a significant extent, the consequence of it was in 1966, Nobel Prize in Chemistry was awarded to Robert Mulliken for his creation of molecular orbital theory and its use in the calculation of electronic structure of molecules. And when he was delivering his acceptance speech, Mulliken announced that emergence of computational chemistry as a recognized specialty within the field of chemistry has begun. So this started a new this era in computational chemistry. Then in 1988, Nobel Prize in Chemistry was awarded to Walter Kohn, who developed the density functional theory, and John Pople, who developed the use of computational methods in quantum chemistry. And they contributed significantly to the advancement of computational chemistry. It provided then further evidence that the field already has become a mature, reliable, and essential method of scientific inquiry. Now, today we can see there are plenties of literature where computational chemistry has become one of the focal point of and then there are large number of courses, academic programs in undergraduate and post this graduate, undergraduate these levels are available. I have seen there are numbers of online courses are available at different these platforms like edX, Coursera, and others. These are all the outcome of all these things. Now, this technical breadth of computational chemistry and its interdisciplinary nature and its applications make this now this subject is becoming subject is taking more and more these complex problems, and now it is becoming challenging for our researchers to apply the computational knowledge, because computational knowledge has also significantly this expanded and developed in the last few decades. And this computational chemistry now, it can be defined as an attempt to model chemical and biochemical phenomena, that is structure, property, reactivity, by computer implementation of the theoretical principles of classical and quantum mechanical physics. This mostly chemists and biochemists, they are interested in wide array of molecules. So therefore, and with the use of a large number of these computational tools which are available now nowadays. So assessing the strength and weakness of this tool and choosing the most appropriate method for solving these complex problems. Now, this is a challenge for this computational chemist. If we look at the fundamental level, chemical phenomena are determined by the valence electrons. This is governed by the laws of quantum mechanics. So the first principal approach to chemistry, that would require solving Schrodinger equation for the chemical systems under study. But Schrodinger equation, the problem with it is it cannot be solved exactly for multi-electron atoms or molecules. So it is necessary, it has become necessary to develop a variety of mathematical methods that made approximate computer solution or equation possible. Hartree-Fock approximation was there. Then there are significant, this development in the form of this other technique like semi-empirical quantum mechanics, then density functional theory, classical computational method, molecular mechanics, molecular dynamics, Monte Carlo simulation. So a large number of tools and techniques are nowadays available. So with this, I believe that today it's the right time because of this phenomenal growth of information technology and computational science. Right time, right golden opportunity for persons engaged in chemical research and research in chemistry to make these subjects, more formidable in handling all the complex chemical problems. And I believe that all the participants over here, they will be benefited at least to certain extent in understanding the essence of these subjects from all our expert members who will be delivering their these lectures here. And and there is no dot of these resources available. So my advice to all the participants is, after you get the preliminary, basic, fundamental, or substantial information out of this FDP, you try to learn further from different online resources. And I can assure you that there are large numbers of resources available. If you just go to internet and search, you'll find that numbers of courses, numbers of programs are available in this area. So this is the time of self-learning, and only we are trying to create an atmosphere for enthusing yourself or making yourself more, tempted to adopt these techniques of self-learning further for your own intellectual development. And I believe that in near future, we will have a significant numbers of computational chemists available with us. So to take care of these complex chemical problems of the which are existing at present and of course of the future. And with this, my best wishes to all the learners for a very effective and productive learning. And my sincere thanks goes to the resource persons for accepting our invitation, for presenting their, their knowledges, their experiences before our learners. This is the one of the biggest advantage of the present scenario, because as we have embraced this digital culture for sharing of knowledges in this pandemic scenario when people are confined at their homes. So this has broken the barriers of time and space, and at the same time numbers also. So at any point of time, we can a large number of participants can assemble. Experts from different corners of the world, they can be made available. And this is the great thing of our digital this technology. And we are trying to take the maximum benefit of this technology. And my congratulations again to all these faculty members, Dr. Somazdar, Dr. Taposh Ghosh, and all other associated with natural applied science to make our this planning, our vision, our thought process effective and implemented. So with this, I'd like to conclude. Thank you for inviting me and for allowing me to share my views. Thank you all.
Sir, if I may request you, would you please launch the abstract book for today's FDP session, please?
Yes. How to launch it?
So just maybe
Dr. Ghosh, yes, you put it up and let him
I request Dr. Bach to share his screen, please, with the abstract group.
Yeah, I'm sharing. Is it visible?
Yeah, it's coming. So
So I'll
yes,
just scroll
it's
down it.
visible. Yeah.
Yeah.
Okay, the book is now visible. So I am declaring it, this open, and it will be made available to all the participants who will be who have joined already to this FDP program. Thank you again for taking up this initiative. This is also new things, and of course, uh, as the days progress, we are innovating new and new things to make all this digital, this learning process more effective and more attractive to all the participants. So we can see the book. This is the book of abstracts, and lectures also will be, I think, available with our this webinar team, and those who are interested, they can have access to the lectures also. So so this is one of our good initiative or good practices, particularly in this context, and I believe that this will be of this a point of attraction, or this subject of this would an interest to all the participants over here. Thank you for Dr. Samazdar and your entire team for taking up this initiative. Thank you.
Thank you, sir, for formally inaugurating the book of abstract for the FDP, and this will be available to all the participants who have registered with all of you, and in very quick time. Thank you, sir, again for sharing your thoughts and giving inspiring views on the opportunities of computational chemistry that lies ahead, and the advices, very important advices to the learners of chemistry and material sciences like us, how to thrive into the field of computational chemistry, and definitely it will be a good motivation for us to think about that. Thank you very much, sir. Thank you. So may I now request Dr. Mona Lisa Char to take over from here and do the moderation for the session. And over to you, Dr. Char.
Thank you, Dr. Ghosh. Okay, now all of us know. Okay, so moving forward with the session, may I now request our Director, School of Natural and Applied Science, Professor Dr. Shukhendu Somasdar sir, to address all the participants and give his introductory remarks about this 5 days faculty development program on computational techniques in chemistry and material science. Sir, please.
Thank you, Dr. Char. Let me share my screen. Namaskar, Honorable Vice Chancellors, distinguished guests, our panelists, respected panelists, and all the participants. It is a privilege to represent Maulana Abul Kalam Azad University of Technology in my association with the School of Natural, Applied and Social Sciences. I, on behalf of the university, as well as the team and my own small behalf, would like to extend a sincere, warm welcome to you all. This 5-day-long session of intellectual stimulation.
Excuse me, sir, your voice is breaking, sir.
Okay, now, is that okay now? Is it better?
Yeah. Yeah.
Yes, sir, yes, it is better, sir. Please, sir.
Thank you.
Yeah.
Honorable Vice Chancellor, sir, set a very historical and relevant context of the area of the program. So there is very little to add to that. What I would like to do is twofold. Essentially, I would like to introduce the school and then a little bit of the background or the canvas, what we are going to be involved in during this 5-day session. So this is the School of Natural, Applied and Social Sciences. We used to be known as Natural and Applied Sciences, but from this term, we are introducing some social sciences as well. This is essentially the structure of the school. And we have departments of applied science, material science and technology, Department of Forensic Science, and there is one social and behavioral science that is the most recent addition, and there are several courses and programs that are on offer. These are the uh, these are the courses that are on offer in this term, and there are 13 of them in total. As Dr. Ghosh has indicated, and Honorable Vice Chancellor, Sir, underscored, the academic focus of the school and the constituent departments of the school are twofold. In this case, it is computational science of materials, and the other part is nanoscale investigation of materials. That does not mean that we neglect everything else. However, these are what one may call our focus areas. And the organizational focus, there are two aspects of it. One, just a sec. The growth. As one can see, that the school is growing fairly fast. In the year 2018, there was a single program in MTech in material science and technology. And in this year, there are 13. The number of faculty has also grown. However, we are not growing at the cost or at the expense of quality. We are trying to maintain quality as well. Among our faculty, there's one Alexander von Humboldt Fellow, one Nehru Cambridge Fellow. There are doctorates from the University of Michigan, Ann Arbor, Indian Institute of Science, Bangalore, and institutes of repute like that. There are multiple GST grants and quite a few publications in high impact factor journals that one can be proud of. But also we have amongst us several very senior office bearers from professional societies such as Institution of Engineers, the Electron Microscope Society, and the like. And this is our scoreboard so far. The university, I am proud to say, that is perhaps the unique in the world which has conducted more than 300 webinars during this so-called lockdown. Instead of shutting down or slowing down, we actually have geared up a notch or two and engaged, encouraged, and educated the learning community, the borderless learning community, including ourselves, with a lot of vigor and commitment and compassion together. So the numbers are there. We have done more than 15 online events. There are 1,000 plus hours of online teaching, etc. I don't want to go line by line. That's unnecessary, but you get a bit of spirit of what is driving us, what is keeping, filling our days And our motto basically is doing things together, one for all and all for one. And our modus operandi is dismantling boundaries. There are departments, yes, those are required for organizational purposes, but the nature of science by nature, natural science by nature, is not divided into different disciplines. The atoms, the molecules, the cells, the phases, they do not know if they belong to the domain of chemistry or physics or biology or material science and engineering. It is, these departments are artificial constructs, and sometimes they come in the way of doing true integrated holistic science. In this school, we keep the departments only for administrative purposes, but for the pursuit of knowledge, boundaries do not exist. That is why we are jointly organizing this program. You must have noted there are two different departments. Essentially, we are doing to underscore our realization that science is interconnected. Education and research cannot be separated. They are the yin and yang of knowledge. Physics, chemistry, biology, mathematics are connected to each other and enabled and empowered by the development of computational ability and computational power and the user friendliness of computers and their application in recent time. So let us come to the fact of the matter. I'm now gradually moving out of talking about ourselves and phasing in talking about the areas where light would be thrown today in different uh, domains, deep and specialized fashion. If we look at the material world, we see small things get together and build larger things. And those larger things again get together and make systems. There seems to be actually some principles at work. And if we give a little bit of thought, we see there are 5 cardinal principles at work in this world. First one is assembly or organization. Atoms get together, they organize them, they assemble, they form molecules. The molecules forms, let's say, cell organelles form cells. And it is not just limited to biosphere. It is limited in the inorganic world as well. Examples could be given. Now, in this organization or assembly, it is done, there is order. The assembly is not done, is not in a disorderly fashion. Of course, there could be disorder. We call those materials amorphous. So there is order. There is one way of assembling self-assembly, which is ordered self-assembly. And the other one, that is basically the ordered self-assembly is the focus of a lot of scientific studies. Then we see the scale in space as well as in time. For example, atoms are rather small scale, then the molecules, then the cells, tissues, etc. And the movement of at the smaller scales are also at very faster. So the behavior of these materials, if I may call them, these constituents, in time also in some way related with a spatial scale. The movement of the atoms are much faster than the movement of a large gorilla. That's related. So we have scale in both space and time. Then we have hierarchy. What is hierarchy? Hierarchy is basically, as we see, for example, cells, they are organizing into an organized unit called tissue. Now, this tissue, an organized unit, it acts itself as the building block of organs. That is a building block for an organized unit at a higher scale. So, organized unit at a lower scale acting as building blocks for higher scale, that is hierarchy. And finally, exceedingly importantly, is emergence. That is from a lower or smaller scale, it is not, and I underscore it, it is not possible to predict the behavior in a larger scale. For example,
Yes. Yes.
it is, for example, we can know a whole lot about the hydrogen atom and oxygen atoms, but when an H2O molecule, we can be able to predict. However, when zillions of H2O molecules come together, a property that is liquidity of water, they emerge. So this is essentially whatever we do with materials or matter, these 5 points is always in the back of our mind. And as time progresses, as Honorable Vice Chancellor pointed out, that the paradigms have changed. For example, initially there was this trial and error paradigm or empirical science. And they by no means that was anything less. At that time, that was the cutting edge of science. People like Presley, Lavoisier, Faraday, that was their modus operandi. Then came the second paradigm of model-based theoretical science. An example could be the first law of thermodynamics. And again, Schrodinger's, Maxwell, Bose, they are contributors in this paradigm. Subsequently, the third paradigm is computational science, where it comes, and there are models such as density functional theory, molecular dynamics. And right now we are, it seems to be, in the fourth paradigm of big data driven science. Here down the data is here. In the third paradigm, some underlying physics and chemistry was the guiding or the driving force. Here, the fourth paradigm, a large part of that has been taken up by the data. Data, from data to insight, that is essentially the keystone of this fourth paradigm. So this here for materials informatics, the science of materials with materials, machine learning in the science of materials. These are areas which form in the fourth paradigm, as well as what we are going to talk about today. I mean, and in during this entire FDP is comes somewhere in the third and the fourth paradigm. So the running summary basically that scientists are constantly striving to advance their ability to understand, predict, and improve materials properties. That's the objective. Due to high cost of traditional trial and error methods in isolation, scientists are increasingly relying on simulation and modeling methods to understand and predict materials properties a priori. Materials informatics is a branch of the science of materials that utilizes high throughput computation to analyze large databases of materials properties to gain unique insights and discover new materials in real time. More recently, data-driven methods such as machine learning have been adopted in materials informatics to study the wealth of existing experimental and computational data in materials science, leading to a paradigm shift in the way material science research is conducted. Here I come to the central dogma of the science of materials. Essentially, human needs and desires, they require performance. Whatever it is, for example, the computer or the implements in the kitchen, what we are interested in, whether it can perform what its purpose, what it is meant for. And performance is essentially governed by the properties. So the computer screen is made out of, say, Gorilla Glass. Its properties are different from the kitchen implements. Many of those things might be made out of plastics or metals, aluminum and steel. And these properties, in turn, are determined by structure. Structure, again, is essentially what governs most of the things in materials at different scales. And also, how can we achieve the structure, the desired structure? We have to basically play and tweak and identify and pin down the composition, the right composition and processing of the materials. So from the engineering point of view, we go in this direction. Essentially, first, the designers or the users, they specify the performance. And then scientists and researchers move in this direction. Here you see this is many to one. So there are many processings might lead to one structure. Many different structures might give more or less the same property. Many different properties might serve the same purpose. However, going this direction is somewhat tricky. So these are inverse models, basically, that is done through materials informatics and machine learning. These are forward models where the property is expressed as a function of composition, processing, and structure. And modeling, more or less, this is where the domains of modeling. So when the moment we express something as a function, we are gradually entering the arena of modeling. Now the structure, we need to keep in mind that they are like these Russian dolls. That is hierarchy. There is structure at lower level, for example, atomic structure. Then comes crystal structure. Then there are defects in crystals. So those are structural aspects as well. Those polycrystalline, there are many crystals together. There is structure as well. So this structural hierarchy is critically important. So the scale and hierarchy, we need to keep that in mind all the time when we are working with models, because the natural laws, the laws that are governing the behavior of materials, they are different in different scales. In a very small scale, around here, it is quantum mechanics. In the large or the standard human scales around here, it is classical mechanics. And the transition takes place gradually. Scale and hierarchy, whatever we do, whatever modeling techniques, whatever computer software, whatever programming language we are using, we need to keep this in mind all the time, the scale and hierarchy. So to summarize that the multi-scale structural information, the materials are multi-scale hierarchical complex systems. Materials behavior is typically scale-dependent emergent property. Emergent means it is not always possible to predict in advance, knowing from a reductionist approach, knowing the constitutive equations at a lower level of association, lower level of assembly. It is not always possible to predict what is going to happen at a higher level of assembly, at a hierarchically higher scale of assembly. Then governing equations are valid only within relevant range of scales and are meaningless beyond. And reductionist predictions across scales are best to be avoided. And a very famous phrase coined by Phil Anderson, more is different which also implies equally emphatically less is different. Today and in the coming few days, maybe you would be exposed to techniques and of modeling techniques which focus on a small scale, like nanometer scale. So not just more is different, but less is different as well. So multi-scale modeling is the order of the day. We cannot think of a model, a computational technique, which is which is universal, which is basically pan scale. So different scales, there are different modeling techniques. There are DFT, molecular dynamics, all these things, and there are experts. They know much better than I do about this. So I'm not going to even elaborate even for minutes on this. Just a overview graph here. So based on all this, how is the knowledge constructed? So this is a conceptual nutshell of how the process. Essentially, we are engaged in science and technology. Science, it's teaching, learning, as well as research. The idea is to create and generate knowledge. The knowledge creation process, it actually requires theory, the laws of science, understanding, but however, it starts from data, experiment, observation, literature, database. If we go back to Newton's times, to Galileo's times, to Kepler, Copernicus, it started with data, experiment. Observation is experiment as well. Then there is correlation. Patterns are recognized on paper and now on screens or in the cloud, so to say. So there are inference engines now, they are sophisticated ones, but maybe a century ago, the human brain acted as the only inference engine. And these two together, the data and the correlation, the inferences, this is an inductive approach. Knowledge creation always takes place in an inductive way. Then the laws of science, they validate them, they generalize them from the specific. Today, we have a plethora of data, big data, and there are different techniques such as neural network to use as inference engine. There is data sciences, how to correlate among large data. So that's there. Tools are there. However, the principles are not recent. These are classical principles. Now, modern techniques are being adapted. In terms of data, it serves us well to always remember that data, especially in the science of materials, is rather heterogeneous. It can be a microstructure, it can be some spectrograph, it could be physical properties, n number of things are there, chemical properties. So heterogeneity of data and hierarchy of data, these poses complexity problems, make things complicated, and computers and computational power becomes essential. We cannot really handle things at in this large scale, in this entire the gamut of hierarchy without computational power and collaboration. The power of network, the collaboration is of crucially important as well. All together, all these things, they do go, they act together, and we almost like a funnel like process, knowledge discovery takes place. And this knowledge discovery is, this process is being adopted, let's say in pharmacy, drug discovery processes, and also in materials discovery processes, and across the entire gamut of what I call science of materials, which encompasses all these areas. This conceptual architecture of research on science of materials in the age of computational intelligence. Essentially, there are theory databases are available, combinatorial libraries are available, and imaging libraries are available, and there are integrating tools. This is where the computational power and user friendliness of computers, they play a very important role. This is an overview, a schematic overview in the different sessions of this FDP. Different, the focus, the searchlight would be focused on different areas of this overview, and you, all of us, would learn more and in a deeper fashion in some well-defined, specialized areas of this. What I'm trying to do here is to again show you the contours of the canvas in the background on which different paintings are going to be drawn in this course of this. Essentially, the focus of science of materials is matter. And the source of natural or artificial intelligence is information, information processing and communication. The transformative power of computational tools of learning emerges from the synergy of integration, inclusion, and interaction of ideas and individuals. And in the 5 days starting now, we would be engaged in these 5 eyes. Thank you very much for your time.
Thank you, sir. You really made my task very easy by giving such a nice introduction about our school, the Natural and Applied Science, and the whole program, the 5 days, this computational program. Now, moving forward, all of us know that such a long 5 days program could not have been possible without the combined effort of all the participants and the persons on and off the screen. So we all are very thankful to everyone. On this note, I would like to request Sri Kalipada Das to address the vote of thanks.
Thank you, Mona Lisa. Am I audible?
Yes, sir.
Then clear.
Respected dignitaries, ladies and gentlemen, a very good morning to you all. I deem it to be a great pleasure and pride privilege to extend my sincere thanks and gratitude to all the distinguished speakers as well as panelists and the participants who have joined with us for the online 5 days faculty development program on computational technique in chemistry and material science, how to use contemporary software tools, organized by Department of Applied Science and Department of Material Science and Technology under School of Natural and Applied Sciences, Maulana Abul Kalam Azad University of Technology, West Bengal. At the outset, on behalf of the organizing committee of this FDP program, as well as on my own humble behalf, extend our sincere thanks and gratitude to our Honorable Vice Chancellor Sir for his leadership from the front is always inspired us. We are very much grateful to you, sir. Thanks to our director, Dr. Shamazdar, of Applied and Natural and Applied Science, School of Natural and Applied Science, who always guiding us to run the activity of different departments under the School of Natural and Applied Science. Thank you very much, sir. And also today you have set a very good for this 5-day program. Thank you very much, sir. Thanks to the Vice Chancellor who has sent his good wishes, the Vice Chancellor of Islamic University of Science and Technology, who is our equipped training partner. Thank you for his best wishes. Thanks to the total, the coordinator as well as the total team of the TQIP 3, who has always helped us to arrange this program. Thank you all the TQIP team members. Thanks to all the faculty members, directors, head of the Department of Maulana Abul Kalam Azad University of Technology and its students, as well as the faculty and students from various affiliated college, as well as other universities like Vishwabharati University, ISR Kolkata, Kazi Nazrul University. My sincere thanks also to all the speakers who will be deliberating the next 5 days program, and also the team who is behind the scene to facilitate the infrastructure of this particular technical program. I am meaning the webinar team of Maulana Abul Kalam Azad University of Technology. And as I already mentioned, that the speakers who will be there in the next 5 days program, they are from IIT Roorkee, Indian Association for Cultivation of Science Kolkata, NIT Sikkim, IIT Indore, as well as who is there present in our first session program, Dr. Achinta Kumar Datta from IIT Bombay. Thanks to others, if I miss to mention anybody who have also helped us directly or indirectly to make this program a grand success. If I do not mention the total organizing team of this 5-day FDP program, mainly the convener, Dr. Taposh Ghosh, as well as the course coordinator, Dr. Arjit Bag, who has also worked hard to make the program a grand success, and all the organizing team members of this particular webinar, this FDP program. Thanks to all once again. Thanks for giving me a patient hearing. Thank you.
Thank you, Mr. Das. Now, before moving forward, let me brief out all the sessions of this 5-day faculty development program. There will be 6 lecture sessions and 5 hands-on sessions all together in these 5 days. Every day, there will be a feedback form which will be circulated. The link will be posted in the box, and I request all the participants to please fill that feedback form and submit at end of each day. On last day, that is 19th September, Saturday, we will post one questionnaire with MCQ based on the whole 5 days session. Kindly fill that questionnaire and submit it. During the sessions, participants are requested to post their queries in the Q&A box. It is below the screen, which will be discussed by our experts. Now I request Dr. Arjit Bag to introduce the first speaker, Dr. Achinta Kumar Datta from IIT Bombay. And now onwards, I hand over the session to Dr. Bag.
Okay, thank you, Dr. Chair. I am extremely honored to introduce today's speaker, Dr. Achinta Kumar Datta, Assistant Professor of Department of Chemistry, IIT Bombay. Achinta Kumar Datta is an emerging theoretical chemist of our country present day. He did it MSc from Vishwabharati University and then do his postdoctoral work under the guidance of Professor Dr. Saurabh Pal, who is present director of ISR Kolkata. And Dr. Datta has completed his PhD in 2014 and then moved to the Max Planck Institute of Chemical Energy Conversion of Germany for his postdoctoral work. And coming back from Germany. He joined IIT Bombay as assistant professor. His research work mainly on development of theory and implementation of theory, particularly the QMM arena. So now with that brief introduction, I request Dr. Datta to deliver his talk. Dear Dr. Datta, please. Hello, Dr. Datta, are you getting?
Yes. Okay, let me ask the first usual question that am I audible?
Yeah,
Yes.
yeah, audible now.
Okay, now I ask the second question. Is it visible?
It is visible. Okay, please go ahead.
Okay. Uh, Thank you, Professor Bag, for giving the kind introduction. I am very much honored to present in this faculty development program. So today I'm going to talk about theoretical chemistry, a tool for chemists in the new age. Now, I work in Department of Chemistry, IIT Bombay. So this is how the IIT Bombay looks like. And this is our iconic arch, which says the Sanskrit word Jnanam Param Dhyam. The knowledge is the supreme goal. Now, the moment you think of Bombay, you think of crowded local trains and high rises. But IIT Bombay is far different from that. It's totally green, located at the bank of the Powai Lake, and we have our shares of wildlife. The waters of Powai Lake had crocodiles, and leopards are the regular visitor to our campus. What we have heard that currently there are 5 leopards in our campus. No, don't get scared. They are not man eaters. They are as scared of humans as we are of them. So they are regular visitors. They are just like a big cat. Trust me, I have seen them. Now, I am in the chemistry department. Although science has no division, but I am academically at the chemistry department. I have my degrees all in chemistry, but I'm not like an usual chemist who works in a lab. I rather prefer to work in a computer. So all my work is primarily done in computers. Now, today I'm not going to tell a lot about what I exactly do. What I will try is to give a general view of computational chemistry, its philosophy, its beginning, how it started. It's if you want to understand a subject, it's very important to know its history. If you don't know where from you come, then how you are going to appreciate where you are going. So I'll stick today to the mostly to the history and the philosophy. If I get some time in the end, then I may discuss what I do exactly. Now, as I do in computation chemistry, most of the experimental chemists look down upon us. What he does in computers is not maybe true. And that's a famous quotation of Max Planck that experiment is the only truth. Everything else is poetry and imagination. So in my defense, so what we exactly do is actually poetry. So in my defense, I should say that the poetry is the highest order of literature. So I'm very proud of what I'm doing. But experimentalists looking upon theoretician is not something new. It started pretty early. So one of these French philosophers whose name I can never pronounce, he had written in 1838 that any attempt to use mathematical methods for the investigation of chemical questions must be considered as completely irrational and is strongly opposing to the spirit of chemistry. If mathematics will ever occupy a prominent place in chemistry, an absurd idea that is fortunately completely unrealistic, this would lead to a rapid and irreversible decay of the scientific discipline. Now, if that is true, then what we are doing here? Fortunately, he's a philosopher, he is not a scientist. Philosophers can say anything, but in science, you need to give proofs. And he was proved to be wrong very soon by this strange looking 3 gentlemen. Erwin Schrödinger gave wave mechanics, Werner Heisenberg gives matrix mechanics, and Paul M. Dirac married the quantum mechanics to the general theory of relativity. One interesting thing to notice is that all 3 of them are European. Schrödinger is an Austrian, Heisenberg is a German, and Dirac is a British. So quantum chemistry was actually a predominantly European thing to start with. Now, this is the very famous Schrödinger's cat, and we always discuss Schrödinger's equation, Schrödinger's equation. But remember, what we actually solve in the computer is, although we call it Schrodinger's equation, what we actually solve is more close to Heisenberg formulation of matrix mechanics. So we call it Schrodinger equation, but actually solves Heisenberg formulation. And this is one of the very famous quote of Paul Dirac, which even the Honorable Vice Chancellor was referring to, that the fundamental laws necessary for the mathematical treatment of large part of physics and whole of the chemistry are thus completely known. And the difficulty only lies in the fact that application of these laws lead to equations that are too complex to be solved. So that means everything is there. We know that they are present, only the equations are difficult. So it's almost a problem of time and labor. And of course, he says that part of the physics and whole of chemistry, he was a physicist. So of course, he looked down upon chemistry. His less well-known part of the quote, this quote actually goes on, then hence it would be desirable to develop practical approximation schemes for the application of quantum mechanics. So this is the beginning of approximate quantum mechanics, what finally leads to computational chemistry. But up to the Dirac, it was whole computation quantum mechanics. There was no quantum chemistry, as well as computers were of course not there. So there was no computational chemistry. The quantum chemistry actually started with Linus Pauling, the great man who has actually won Nobel Prize twice, one for chemistry and one for peace. And he is very famous. He actually worked on many things, even on biological systems, but his pioneering contribution is the molecular orbital theory. And to me, his more interesting contribution is that he has written his first book on quantum chemistry, that is Introduction of Quantum Mechanics with Applications in Chemistry. If you search online, you can still find that book. This is the first book of quantum chemistry to start with. Now, many of us has read molecular orbital theories in our school chemistry classes and drawn those MO diagrams like this one. But remember, they can only be drawn easily for diatomic molecules. The moment you go beyond diatomic molecules, you cannot just do calculations by hand. So there comes what is computers. And just to remember you what exactly computer is, we all use as computers, but in a crude sense, that is a engines. It is made of gates which actually process the numbers 0 and 1. It can be either 0 and either 1, and this is a logic gate. So logic gates actually operates on 0 and 1. Of course, these are classical computers. Quantum computers can have 0 and 1 at the same time, but in classical computers which we have used, generally actually operates by that. So this is actually a model, but we have sophisticated computers like IIT Bombay has a supercomputer with 1 petaflop of peak speed. So computers has become tremendously powerful today, and all of us know the Moore's law, which approximately translate that in each 2 years, the number of transistors in a chip doubles. At the same time, the price drop downs. So the way computers has become cheap, it's become amazing. So when I joined my PhD almost 11 years back, the best machine available in my institute only have 16 GB of RAM. That's a big, powerful supercomputer. And now my laptop itself has 16 GB. So it has evolved like anything and it has become cheap like anything. So now you have the theory, you have the computers. What was missing was the man. And there comes John Pople, the pioneering chemist and Nobel laureate, Sir John Pople, to be really honest. He first developed the first general purpose quantum chemistry program, Gaussian. Many of you have heard the name Gaussian. It comes due to the fact that it uses Gaussian type of function to actually evaluate integrals. That's where the name Gaussian comes from. And of course, Pople was an academician. So when he developed the software, it was distributed for free. He gave it to anybody it wanted, and it used to get distributed to QCPE, Quantum Chemistry Program Exchange, for free. And in the background, it shows one of the source code punch cards. So that were the generation of punch card. To be really honest, even I did not see punch card. I seen magnetic tape, but punch card was a trend before I born. So I did not see it, but that time the programmings were written in these punch cards, and then these punch cards were processed. So this was a free software. And because of this pioneering contribution, he actually went to win the Nobel Prize with Walter Kohn. Now, in 1987, the idea of commercialization and market economy came forward. So it becomes a commercial organization 1987, and they started to sell it for money. When people protested that, okay, my science is for free, it's not for money, like everybody should have an access to a scientific thing. They did not agree, and what they did is to ban people from using Gaussian. Now you see the fun part. So the the company managers were all his former students, and the students actually banned the professor who created the software that no, you cannot use it anymore because we want to make money out of it. So that is one of the saddest day in the theoretical chemistry as well as in the science that day, where the money won over loyalties and academic freedom. Of course, and then this come from banned by Gaussian. So those who competes with Gaussian or write computers program which are faster or competitive to Gaussian, they cannot use the software program Gaussian. Now, to some people, it's a source of great honors because that means they are in the big league. One funny thing is that actually nobody from India is banned by Gaussian. So which shows actually in a sense that we are not important enough. They only ban big people who they conceive to be threat. And unfortunately, from India, still they did not consider anywhere to be threat big enough. But you never know. Maybe one of you can one day become banned by Gaussian and actually join the big league. Of course, you cannot stop knowledge by banning people. So when Gaussian got banned, many other computational chemistry software packages are available. And if you search in the internet to Wikipedia, you will find a big list of it. I'm naming a few only: Molcast, Molpro, Turbomol, QChem, PQS. And the last one, Orca, is my favorite due to personal reasons. We'll come to the features of Orca at the end part of this lecture. Now, we started with a boundless pessimism. Now it's the time for boundless optimism. Enrico Clementi in 1975 started claiming we can calculate everything. Now, he was born in 1931, almost 90 years old, and still very active. I had the good fortune of meeting this man once, I think 8 years back. He came to India, and he is truly an inspirational man. But in some sense, he is as wrong as the French philosopher of whom I talked in the beginning. No, we cannot calculate everything. Even almost 45 years of his statement, we still cannot calculate everything, and everything cannot be actually calculated. But remember, even we cannot calculate everything, we can actually calculate a lot of things. So what we can calculate? We can calculate quantities that cannot be measured. So if you have an intermediate which is very short life that it immediately get converted, or you cannot get enough amount to measure it, you cannot calculate about, you can predict about their properties by doing computations. Experiment gives you observable. It just tells what happens. It does not tell how it happens. But what quantum chemistry can tell you, it's why it happens, how it happens, not only what happens. So it can help you interpretation of the results. It can help you to get trends in the results. Many times we do experiment and get a lot of results and we don't know what is the trend. Theoretical chemistry can help you to understand the trends in their results. Of course, it can predict the outcome of the future experiment. If you can do the computational chemistry real fast, and most of the time experiments are very laborious. You see at experimentalists the hard work in hot weather in front of furnace they spend. Doing computational chemistry is easy. You sit in air conditioned room, work in front of laptops, and they are fast. So you can actually predict a lot of the experiment. Question is how fast and how accurate. But these things are becoming easier days and days, and it's becoming more and more accurate. So these days, to do drug discovery, most of the time they apply computational chemistry. So drug companies actually employ a lot of computational chemists who first do the calculation and tell that a molecule is probable drug or not. If they pass the test, then they only do the experiments. Otherwise, they don't do. But to me, the computational chemistry in the synergy of experiment actually leads you to the whole truth, the entire picture, which you cannot do just from experiment or just from computational chemistry. If you use them together, then only can you see the big picture. So how the computational chemistry works? So the way we'll start is that we'll start from very basic, what we all know, and then we'll see into more details. So let us take this diatomic molecules. It's N2, and from our school knowledge, we know that N2 has a triple bond, and the highest occupied orbital is of sigma type, so they are very inert. And actually, a lot of research goes on how to activate nitrogen, because remember, nitrogen is very important for fertilizer, for explosive, and many things. And a big part of our body is made of nitrogens. So this is a nitrogen molecule. Now, if I just want to define it classically, no quantum mechanics, just from classically, we just need two laws. First is Coulomb law that tells how two charged particle interacts, and this is the statement. So here we have two charged particle, two nucleus and two electrons. We know the electron will repel and nuclear will repel, but nuclear electron there will be attraction. And second thing is the kinetic energy that comes from the Newton law. So if you just know two laws, then it's very simple. You can write the total energy as the sum of electronic kinetic energy, nuclear kinetic energy, electron nuclear attraction, nuclear repulsion, and electron attraction. So this is the classical way of doing it. That means if you just stick to Newton, so what happens is that in classical mechanics, Newton's equations are solved to find two things. First is the position of the particle with respect to the time, and second is the momentum of the particle with respect to the time. The solutions are actually called the trajectories of the particle. So you want to know how the particle is evolving with time, where the particle is at time t, and what is its momentum. That's the thing you solve in Newton's equation. Problem is that in quantum mechanics, due to the uncertainty, you cannot do that. You cannot precisely tell the position of the particle and their momentum at a precise time. So you just work with probabilities. Now, so although we call of a Newtonian mechanics, there is a Hamiltonian formalism of Newtonian mechanics, which actually readily translates you from the classical mechanics to the quantum mechanics and the Hamiltonian of the system. So Hamiltonian, when you talk of Hamiltonian, most of the time we think of Schrodinger equation, but remember Hamiltonian can be classical also. Hamiltonian has nothing to do with Schrodinger equation. It can be classical Hamiltonian also. It has to do with equation of motion. So Hamiltonian of the system correspond to the total energy. If I go to a classical Hamiltonian, then that will be, as I shown before, it will be kinetic energy plus potential energy plus electron nuclear attraction, electron repulsion, and nuclear repulsion. And you can actually calculate them very precisely using classical mechanics formulas, and you can find out what is the energy. Now, if you are interested into going into quantum mechanics, then you start with the classical Hamiltonian. First, what you do is that you convert everything to atomic units so that your equations looks less clumsy. So that means you put the charge of the electron, mass of the electron, everything to as one. And then what you do is that you replace the momentum in a classical Hamiltonian by I Laplacian, and your position x by a quantum mechanical position operator. That's the two transformations. So you transform your momentum p to a quantum analog and also position to its quantum analog, classical position operator x to its quantum operator x. So that is just the two transform. So the only two transform exist from classical mechanics and quantum mechanics. Once you do the transform, so first you write the classical Hamiltonian, transform into its quantum variant, and then you are all ready for doing quantum mechanics. Of course, one other thing we know is that the spin of the electron. Now, it's important to notice that the original Schrodinger equation does not have any spin. It does not tell anything about the spin, and in Schrodinger equation there is actually nothing called spin. So spin is only inherently present in a relativistic formalism, that is Dirac formalism. In Schrodinger's formalism, there is nothing called spin. But we already knew that electrons are antisymmetric. So we just put the spin by hand, by brute force. So when we say spin, there is nothing unique about spin. That is an ad hoc addition. In quantum mechanics, in Schrodinger formulation, there is nothing inherent spin. So now I go to Schrodinger's equation, and that is the less popular version, where the time dependent one, where my Hamiltonian depends on time. So it depends upon x, r, and time. But if the Hamiltonian does not depend upon the time, which is most of the cases, I go to the time independent Schrodinger equation, which is more popular. And if I solve it, I get the energy. So the recipe you see very simple. I write classical Hamiltonian, I convert into quantum mechanical Hamiltonian, and then I solve it to get energy. Now, what this energy actually is? Of course, before I go to energy, I get to the many particle wave functions. And I have the interpretation. So they are basically the Copenhagen interpretation of quantum. Quantum mechanics has many interpretations because it's not observable. It is nothing to do with the classical world we look. So the interpretations are not unique. So one of the popular one is the Born interpretation, where at the for a particular position for a particular nucleus separation x and for a position r, I consider the wave function square as my interpretable quantity. So psi square is the only quantity which I can interpret. That is the probability of finding a particle at a position r. And second thing is Pauli principle. So that essentially tells that if I interchange the position of two fermions, the sign will change. The sign will become negative. So that is the Pauli's antisymmetry principle, although the popular version says that it essentially means that two or more fermions cannot be in the same orbital. That's not an exactly correct statement. The correct statement is that for fermion, if you interchange the coordinates, the wave function will change its sign. Now the question is that how I can picture this wave function. So what wave function has? Wave function has three coordinates, x, y, z, and one fourth coordinate, that is spin. So that means, can I visualize this? The answer is no. So if there is an electron, that means I have 4 n coordinates. Now human brains cannot think of more than 3 dimensions. So you are talking of 4 n dimensions? No, we cannot think of. That is simply impossible. So you cannot visualize the wave function. What you can just calculate is the wave function square. That is a probability. So nobody can actually intuitively picture a function of 4 n variables, and then that means the insight has to come from somewhere else. So just looking at the wave function, you don't get any insight because there are 4 n variables and you don't know how to do about it. No human beings can think of a 4 n variable system. And now the next question can come, okay, then what about the orbitals? The blobs we see in chemistry textbook, the spherical one, s orbital, the dumbbell shaped p orbital, the double dumbbell shaped d orbitals, what are they then? Well, they are just one particle wave function. They are strictly true only for hydrogen atoms. For everything else, beyond everything hydrogen atoms, they are approximations. They are not how they look. They are one particle representation of the exact wave function. So next time when you see orbitals and people try to do a big amount of conclusions out of it, always remember they are just approximate pictures. There is nothing measurable called orbitals. What you can measure only psi square. That's the probability. Now, what about the total energy then? So what this total energy I get from the Schrodinger's equation, it's nothing but if I suppose I take a molecule and fragment them into its constituents, what a molecule constitute of? Electron and nucleus. So if I fragment the molecule into all the electrons and nucleus and send them long apart, so the energy what we'll need to make them molecule again is the total energy. So that's why it is always negative, because if you bring them together, they will get stabilized. Question is that, can you observe energy? In principle, yes, energy is unobservable, but in practice, no, you cannot measure energy, the total energy. What you can measure in chemistry as well as in every sciences is difference of energy. Be it thermodynamic property, enthalpy, entropy, or spectroscopic properties, energy difference, excitation energy is that one. Then what is the relevance? Because we can calculate the energy difference, we can get spectra, we can calculate energy difference. That's why it's so important. Now, the question is that how much is the molecule's energy? So, chemists generally prefers EVs. So, if you have a small transition metal complex, it's 10,000 to 1 million EVs it can be. Now, how much accuracy do we need? So, if I have a complex, it can be 10,000 or maybe a lakh, a million. That will be the energy. Now, how much accuracy we need in the energy difference? So the chemical accuracy is 1 kilocalorie. Just to remember it, what is the energy? So the physicists love the atomic unit. What is AU? Chemists love the 20, sometimes the EV or the kilocalorie. So this is the conversion. Now to make your result meaningful, the energy difference to be meaningful, you need energy difference which is in the order of 1 kilocalorie per mole. That means if you convert to EV, it's 0.05 EV. So that means a poor computational chemist is supposed to generate accuracy what is more than 1 ppm. So that's how accuracy, that means if you want to predict energy difference accurate, energy has to be highly accurate. So you need very accurate total energy. And of course, when we use Schrodinger equation, we cannot solve it exactly for molecules. Even before trying with any other approximation, what we take is a Born-Oppenheimer approximation. So what the Born-Oppenheimer approximation exactly tells? So again, Born is the same Max Born who gives the Born interpretation, and Robert J. Oppenheimer was the person who was actually in charge of making the first US atom bomb. So that's why he is famous. So what you do in Born-Oppenheimer approximation is that you claim that your nucleus is much more heavier than your electron. So you can actually consider that when your, so electrons is small and fast and nucleus are large. So when you do the calculation, you can assume that nucleus are static because it's slow and electron is moving very fast. Now what is its consequence? Because I think of nucleus as static, I get to chemical structure. I claim methane to be tetrahedral, that only because my nuclear framework does not move. So the whole concept, or I say the water molecule looks like water because its structure is fixed. So my whole concept of chemical structure and the so-called potential energy surfaces comes from the fact that we use Born-Oppenheimer approximation. Second thing is that now my Schrodinger equation can actually solve into two Schrodinger equations. The first one is an electronic Schrodinger equation and second one is a nuclear Schrodinger equation. Most of the time we can work we are interested actually in electronic Schrodinger equation. If we need, we can solve the nuclear Schrodinger equation also, but most of the time it's not needed. Now Born-Oppenheimer approximation works for most of the cases. In some isolated cases, they breaks down and then you are in big trouble. Then so Born-Oppenheimer approximation gives you the concept of potential energy surface. So what exactly a potential energy surface is? The potential energy surface. So see the word potential energy surface. So it's a surface. The energy is the solution of the Schrodinger equation, the electronic energy. So basically this is the surface in which my nucleus moves. So of course you can have local minima, you can have global minima, and you can have saddle points. And so if you take a chemist point of view, a local minima can be reactant and then it goes to the saddle point transition state and then it goes to the product. So you can calculate reaction energies, equilibrium constant by calculating this difference, and you get to reaction rates. You can calculate thermodynamics, enthalpy of formation, all by doing this. Now in computational chemistry, you can actually calculate these saddle points. Remember, these saddle points you cannot isolate experimentally. You can get the minimas, but local or the global reactant and product you can see, but saddle points are not, you can isolate. So that you can calculate by computational chemistry. I think Professor Sumantra Bhattacharya is going to show you how to calculate these saddle points using computational chemistry software. And I must tell you that calculating this saddle point is more of an art than of a science. And I should admit that I am not good at this art. So saddle point for searching is a specific skill which one develop over time. But I think Dr. Bhattacharya will show you how to do that very efficiently. Now next is spectroscopy. So how we relate the spectroscopy to quantum chemistry? So by solving the Schrodinger equation, you get the different state, ground state, excited state, and all the other state. And then you can calculate the transition probability by using a Fermi golden rule, where you have an initial state and a final state and put the Hamiltonian in between. And if you calculate the square, you find the transition probability. And in all spectroscopy, it's a energy versus transition probability what you plot. So you can get to different spectroscopy by quantum chemistry. And spectroscopy, don't forget, actually comes with a different flavor. So at one end of the spectrum, very high end, where the energies are around 14,000 electron volt, they are gamma radiation, which excites the nucleus. Next comes the X-ray, which actually excites the electron from the core of the orbitals. So they give information about the local bonding sites. Next, when it comes to 4 to 1 electron volt, they excite the electron from the valence orbital. So this is where the energy of the valence orbitals lies, this 4 to 1 electron volt. And that's why UV visible spectroscopy is very important, because it can describe about most of the chemical processes. That's why, remember, the photochemistry is done with UV or visible spectroscopy, because this is what the energies of the valence orbitals are. So if you want to do chemical reaction, most of the time happens with valence orbital. So UV visible spectroscopy is the tool to describe the valence orbital. Now, as you go to lower energy, it can no longer excite the valence electron also. So then it starts to excite the vibrational degrees of freedom of bond, and you lead to IR or Raman spectroscopy. You go even lower, 10 to the power 4 to 10 to the power minus 5. It cannot even excite the vibrational degrees also. Now it can only excite or flips, not the excite the electron, but it can only flips the spin of the electron. We know that, of course, one should remember that when we say up spin and down spin, that's a representation. Spin does not mean it's a up or down. Spin is a quantum chemical quantity. There is no classical analog, so we don't know how spin looks like. But we know there's if one is a plus up, then other is the minus up. So what EPR does is that it exchanges the spin, it flips the spin. And if you go beyond that, it can no longer even flip the spin of electron also, but it can flip the spin of nucleus, and that leads to your NMR. So you have a large variety of spectroscopic techniques which are widely used in chemistry, and trust me, all of them can be computed using computational chemistry. And basically, you can take the experimental spectra, you can take the computation, and then try to see and match together and try to understand which peak arises due to what. And that actually helps you to solve problems. And that's what a smart chemists do. Now, thing is that, okay, so we have taken Born-Oppenheimer approximation. Now, can we now solve the Schrodinger equation? Problem is that we cannot solve the Schrodinger equation even after taking Born-Oppenheimer approximation. Schrodinger equation cannot be exactly solved for anything beyond one particle problem, that is hydrogen atom. So hydrogen atom is the only thing where you can solve Schrodinger equation. For everything else, you cannot. So that means you go back to Dirac's philosophy and start taking approximation. So what the approximations are mean? I describe my Schrodinger equation. Of course, I have taken Born-Oppenheimer approximation. Now I can go by two routes. One is a Hartree-Fock route, wave function route. So in wave function theories, I first solve Hartree-Fock. Next slide, I will come to know what is Hartree-Fock is. And then, of course, Hartree-Fock is an approximation. So I miss some things out of it, and then I try to correct for that thing. And that leads me to the, if I correct it exactly, then it leads to the exact solution of the Born-Oppenheimer approximation. That's the wave function picture. A more easy to conceive picture, difficult to do in practice, but in theory, the chart looks very simple. You define the Schrodinger equation. How we define? We write the classical Hamiltonian, convert into quantum mechanical, take the Born-Oppenheimer approximation, and then we are ready to go. So we first solve Hartree-Fock, and then what we miss, we correct for it, and then we go to exact solution. But there's another way, a more popular way, where you don't go into the Hartree-Fock picture, you don't see wave function, you don't solve Schrodinger equation, but you calculate the density of the system. And through the density of the system, there may be a route to the exact solution. So you can get the same information what you get from the solution of the Schrodinger equation by doing this density functional route. We will see how in a short while. But before going that, let's see what Hartree-Fock is. So Hartree-Fock is a mean field model. What do I mean by mean field model? Like in this virtual classroom. So I am there, moderators are there, and participants are there. And of course, some of the moderators I know personally, so there is a specific interaction. Some of them I don't know so well, and some of them I don't know at all. So if one has to describe the classroom correctly, then we have to describe all the interaction. What kind of interaction I have with all the moderators, what kind of interaction participants have with the moderator or the speaker, in this case me, or what kind of interaction the participants have among themselves. But that's difficult to find out, especially if you give a small time, then it's difficult to find out what the explicit interaction. What I can take is an average picture. Say that there is a virtual classroom, this many number of participants are there and they are interacting. I'm not telling who is interacting how. Everybody is interacting. How, I don't say. Still it gives some kind of feeling of the system that, okay, there is some kind of thing. So that's what you do in a Hartree-Fock theory. You take the nucleus and the electron and you consider that the electrons are interacting with each other, and each electron, let's say I have 5 electrons, then each electron will feel the force of the all other 4 electrons in an average way. So if I have 5 electrons, each of these 5 electrons will face the field produced by the other 4 electrons. But I don't know which electron is what, so I see an average field. So it's like the case here, we are sitting in the same classroom, we are interacting with each other, but we explicitly don't know who is interacting with whom and what is the mode of interaction. So the same thing is Hartree-Fock, where each electron is moved in the average field of other electrons. Now that gives you some information, but we still miss how explicit interactions are there. So what we miss is in Hartree-Fock is called a correlation energy. So we were seeing that each electron is moving in an average field of other electrons. What I don't know how each electron is interacting with each other. That's not a strictly correct statement, although I know electrons of same spin, how they interact in Hartree-Fock. I know because of the exchange thing. So if the electrons are of the same spin, again I am showing it upward, but remember a spin is not up and down in that classical sense. So the electrons of same spin, how they interact, it is included in the Hartree-Fock, but how the electron of the opposite spin should interact, that is not said in the Hartree-Fock. And that is called a correlation. So that's the correlation. When I say electron correlation, that means how two electrons interact among each other. So that is like in the classroom, if I say how the explicit interaction is happening, then the explicit statement should be that the speaker is speaking through Zoom or an online platform, the moderator is moderating, participants are listening. That should have been the explicit statement. But in Hartree-Fock picture, there is nothing. You don't have any explicit interactions, and that is what is missing, is called correlation. So it's almost like, so in another way, if I want to say what correlation is, that in Hartree-Fock pictures, the electrons are only restricted to the occupied orbitals. So it does not have freedom to go anywhere. It does not have space. Now, electrons, similar to human beings, like their personal spaces, so they don't want to like to close together. They want to go to the unoccupied orbitals, and that is called a correlation effect. Now, if you think of as Hartree-Fock is a sea of electrons, the correlation is like burst of electrons going out of the sea. And the more intense the burst is, the more short-lived it will be. So the more, if an electron go from a low-lying to a very high-lying orbital, that will be very energetically unfavorable. And the small burst, just one orbital excitation, they will be much more probable. So that's a ballpark idea of what is a electron correlation. I think Dr. Arjit Bagh in the second half will give you more explicit details of how the correlation actually works and what are the ways you can include it. I totally skipped the ways to include correlation. But these days you can do very accurate calculation on electron correlation. And remember, Hartree-Fock alone is not good enough to give chemical accuracy. And how much chemical accuracy we need is 1 kilocalorie per mole. That means beyond ppm level accuracy. So that you cannot get by Hartree-Fock. You need to include these correlation effects. Okay, I told that there is an alternative way. Now, how this alternative way looks like. So here, this is the density plot of CO molecules. Now, what you can see here. If I look at this density plot very closely, I can see the position of the nucleus because of the cusp. And I see which has a higher cusp, so I know which has a more electronegative atom. And if I sum the density over the whole space, I get the number of electrons. So that means once I get the number of electrons, I know how to construct the Hamiltonian. So that means I can construct a Born-Oppenheimer Hamiltonian and I can solve it. So that means I get density, I generate the potential out of it and the number of electrons, and from there I can get the Hamiltonian, and that's what I can solve to get the energy. As simple. But cracks is that if I generate the Hamiltonian, then as well I could have solved it like a normal Schrodinger equation. Why I have to go through a other way? Like I can just pick my nose like this. I don't need to go like this. The thing is that the big fantasy of the scientist is that I will not go into the Hamiltonian picture or the wave function picture. I will just know the density and I will directly go to the energy without going into an Hamiltonian. How it saves us? So the density is depends upon three coordinate x, y, z. It's a three-dimensional quantity. And my original wave function is 4n dimensional. So I cannot solve it. So that's why. So I can actually replace a 4. If I can solve by this way, I can solve a 4n dimensional problem just by 3 dimension, and that's it. Question is that what is the root? And that comes the Weinberg-Kohn theorem. So the first Weinberg-Kohn theorem just says it's an existence theorem. It says that there is a root, but it does not tell what is the root. It just says that the root exists. Now you find out. Second Weinberg-Kohn theorem says that there is a variational approach possible where you take a trial density, you will always get an energy which will be higher than the exact energy. So that means you can use the variational principle to solve it. And actually because of this Weinberg-Kohn theorem, Walter Kohn actually get the Nobel Prize for density functional theory, because once you can get the root even approximately, life becomes so easy for you. You can just solve a three-dimensional problem, and just problem consists of 3 variables, and then you get energy and get everything. Of course, in practice there are complications, but if you know the exact root, then you can actually obtain the exact energies without solving Schrodinger equation. And that's why that is so popular. Now just think about, we are talking about nice methods, what can they do? Now just think about computation cost. Remember, all the computers are fast than human mind. It comes with a cost. Cost is not only the price, not only the money you pay to buy the computers. To run the computers, you need to have electricity, and the computers can get heated up very quickly. So you need air conditioning, and that actually takes a lot of money. So those who are in the business of managing and maintaining computers, so if they know that running a computer for a period of 3-4 years almost have same price as buying the computers, because your air conditioning and your electricity will cost you an hell. So it's important how computation cost is. So Hartree-Fock theory, what we start with is n to the power 4. If you do a little bit of correlation, perturbation theory is n to the power 5, and it goes like this. So if I do this accurate calculations like CISD TQ, it's almost like it will take a lifetime. So if I submit a job today, probably my grandchildren or great grandchildren will be able to see the result provided the Earth survive for that day. Whereas in density functional theory, if you use the tricks properly, you can lead it to an n to the power cube scaling method. So if your system size is n, the density functional theory scales as n to the power 3. So if I go from, let's say, 10 to 100, it will become 100 to the power 3. So basically it will become 10 to the power 6. Whereas if I go to an n to the power 10 scaling method, then the computation cost will be almost impossible to do. So that's why density functional theory is so popular. But again, although we call it n to the power cube, you can, at modern computers with the best program, you can almost calculate like 300, 400 atoms quite regularly. But although the atoms, like molecule size of 300 and 400 atoms can be interesting sometime, but there are many things beyond that. And most of the biological things are, trust me, are real big. So this is an active site of a photosystem 2. I just took the picture from the Wikipedia. I don't have anything to do with it. But that's where the real interest is, the real biology, the real chemistry, how life works. And that you cannot do by any wave function based or DFT based methods. Because although n to the power 3 scaling of the thing is too expensive, you cannot do anything with it. So that's where you come to the multi-layer modeling. That means you use a computational method depending upon what kind of time scale or what kind of time accuracy you are looking at it. So if you are looking at a femtosecond time scale, then you use quantum mechanics. If you go to picoseconds, you can go atomic molecular dynamics simulations. If you go to nanosecond, you get coarse grain simulation, and if you go to milliseconds, then you basically leads to classical thermodynamics or transport phenomenon continuum mechanics simulations. So that means I will cut my cloth according to my budget. So if I have cloth enough for a half shirt, I will cut it like that. If I have for a full suit, then I will cut it like that. Now, one interesting thing is that many of the chemical and biological phenomena actually happens in this interface, the femtosecond and the picosecond. And that helps us to switch to a method where you can use a combine of two, that is a QMM method, where a part of the system you treat in quantum mechanics and the part of the system you actually treat them in molecular mechanics. And so how you do that? So the recipe comes from these three gentlemen, Martin Karplus, Michael Levitt, and Arya Warshel. And they won the Nobel Prize in 2013. Remember, in physics, a theoretician winning Nobel Prize is not a strange thing, it's a norm. But in chemistry, it is very surprising. Chemists are experimental people, they don't really care for theoreticians. And he's the second theoretician to second group of theoreticians after Popel and Walter Kohn to actually win the Nobel Prize. And the QMMM actually which has revolutionized the field. So what you do in a QMMM, you take a big system, you do a particular part which is important where the actual reaction is taking place, the active site of an enzyme that you treat with the quantum mechanics, and rest of the system you treat with the molecular mechanics. And of course, you have to do some special treatment of the boundary where the quantum region is interacting with the molecular mechanics. That means what? Even if I have a big biological molecule, only a part of it I need to treat accurately. Rest of the things I can just treat approximately. Although I need to treat approximately, I cannot neglect it. Then the biology will not come. Biology is not for small molecule anything. All biological molecules are big. So if you have to treat the big biological molecules, QMMM is the way to go. One of the reasons QMMM has not become very popular, although it has a great potential, because lack of software. You have good software for doing molecular mechanics, you have good software for doing quantum mechanics, but you don't have which will marry them together. And that's why they are not black box, even if you have them. One of the solutions can be the newly implemented QMMM code in ORCA, just to tell that ORCA is actually a general electronic structure theory package. It has quantum mechanics, you can do DFT, wave function based calculations, you can do QMMM, you can do molecular mechanics, you can do molecular dynamics, you can calculate actually a lot of spectroscopic property. ORCA was written by spectroscopists for spectroscopy. So you can actually simulate a lot of the spectroscopic properties using ORCA. And the best part of it is that it's fast and can be used in desktop also. You can do a lot of powerful calculation in desktops. Many of the calculations I do these days, I actually can do in my desktop using it. And of course, the best part is it's free. So you don't have to go for any commercial software. You can just download it and start using it in your desktop. So that's how easy it is. How to use it, how to run the calculation, and how to interpret its result using this free software, which I will show in Wednesday in the hands-on session. Just how to use it. Just I wanted to tell that okay, this exists, and most of my research actually involves around this software. So what I explicitly work on is the excited state of very large molecules, which cannot be treated by conventional wave function based method. So I develop new methods which are very fast and can be applied for very big molecules. And also one of the things which interests me is the radiation damage to genetic materials. So these days we are surrounded by electronics, right? And it generates a lot of radiation. And these radiations can be very harmful for our body. It destroyed our genetic material. Don't forget, Marie Curie died out of blood cancer because of she was dealing with radiation causing substances. So what I try to see how this radiation damage happens in the presence of bulk water, because in our body it has a lot of water, and that's why most of the things what we study is actually happens in presence of the water. And what I try to study using QMM methods, how this radiation damage actually happens in our body. These are some representative publications from our group, but that's not important. In the end, I want to thank my group members. So this was sometime in last winter in December, where the coronavirus threat was not there, so we can go out of the campus. Unfortunately, now none of them are present in the campus because Bombay is not in a good shape. But that's how my group looks like, and their opportunity to join the group as a PhD student. IIT Bombay has a pretty robust PhD program. It has a lot of facilities. They support you to travel abroad once. We have a very good postdoctoral scheme. They are quite well paid, and of course, there's a scheme for joining as summer intern, and the summer interns are paid. So you have this paid internship scheme. Who are interested can contact me. And at the end, I want to talk a single slide about the future. So I talked about the past and the present, and of course, we want to know what is there in the future. So in recent years, last 2-3 years, two things has revolutionized. One is the artificial intelligence, big data. So now you see that most of the things these days, you type a mail in Gmail, it starts to prompt you, and that's artificial intelligence. Now, artificial intelligence can really help in quantum chemistry. So many of the calculations what we are doing to find trends are no longer necessary. It can look at the existing data and it can say what will be the exact trend. Second thing is quantum computers. So this is the IBM quantum computers machine. There's a Google Qubit, and many of them are coming up. So this is going to change. So what is the difference between a classical computer and quantum computer is that in classical computer, it can be either 0 or 1. In quantum computers, it can be both. And this speed up the calculation to a limit that many of the things which we think is impossible to do computation. I was talking of my grandchildren seeing the result. With the quantum computers, it may not be necessary. I will myself will be able to see that one. But quantum computers and the artificial intelligence will cause a lot of paradigm shift. So whatever we know, the computer programs we have, the theories we have are no longer going to work on these quantum computers. So we will need a lot of trained manpower to actually write new programs, develop new theories, and do new applications. So quantum chemistry, the quantum computational chemistry is the field which is a great future, both in academia as well as industries, because many of the industries actually hire people to write those programs. So I think there's a great future in that thing. So in the end, I just want to conclude here. Whatever is left, I want to keep it for the hands-on session. So in the end, I want to acknowledge the organizers, especially Professor Arjit Bagh, my student who actually helps me in all the work I do. And of course, the funding agency, IIT Bombay, Inspire, and DSP ACRB. Thank you very much for your kind attention during this long talk, and I'll be happy to take questions.
Thank you, Dr. Professor Achintu Datto, for your excellent and thought-provoking lecture. Particularly, you have started from the scratch, and I think our participants are widely they are coming from different areas. So I think it will be very effective as this is the introduction section. So they will be just coped up with this knowledge of computational chemistry, theoretical chemistry, and all these things. So I think it will be easier for them to go forward with other more technical sessions. So thank you a lot for your talk, which is actually bring from scratch to the frontier research level today. So now we are asking, there is no question. I think there is one question probably. Professor, Doctor, can you go to the question and answer box, please? And I think there is one question I have just.
Or I think we can read it for him. No issue for that.
I think that will be easier if you can.
Okay then.
Read it.
Yeah.
Okay then. So it's from Ananya Bormon. It's she has said that good afternoon, sir. It was wonderful session. Can I get the PPT? I think you are having the YouTube live, so you can have that video as
I
well.
don't mind sharing the PPT.
Okay,
also.
and it's so generous of the speaker that he will not mind the share. So you can have the email ID and then contact him personally to get that. And she's just beginner in the field. She want to know that there is any website from where I can learn about computational work. Is there any tutorials about how to work and which software would be used in this field or should be used in this field, rather say?
Okay, let me stop sharing my screen, and then I think I will
Yes.
be able to answer in a better way.
Yeah.
Okay, first question is that where from we can learn. These days, and even when I was doing my PhD, your best teacher is Google. It cannot happen that you are facing this problem first time in the history of mankind. Somebody else has faced it, and somebody else will face it later also. So if you search in Google, you can find most of the solution of your problem. You are not having sleep in the night, you are not able to do something, you are not able to cook, how to do science, how to do research, everything you can find it in Google. Now, if you ask me about specific examples, yes, there are specific tutorial videos available. If you search in YouTube, there are specific videos available about theories, how to install software, how to run computational chemistry codes. For everything that are available. There is a very nice textbook also. One of them is very famous, is Computational Chemistry with Gaussian. So they come up with a very nice book which accompanies the software Gaussian, and that can show you how to do computational chemistry with Gaussian. To be honest, I myself learned with that book. Like I learned by running things, so that's very easy. About the software, what software you should use, and that's actually like what kind of car you should buy. That's the same question. So it depends first of all on your personal test. I like Gaussian, I like Orca more than Gaussian, but it's my personal bias. And second thing is how much money you have. So there are paid software like Gaussian, Molpro, QChem, uh, and many of them, ADF, Turbomol, and then there are free software, Orca, NWChem. Molcast these days is free. So that you can buy without paying anything. And second thing, what kind of computation you are doing. If you are just want to computation with your desktop, most of these free softwares are good enough. You don't need a expensive software to do your computation. But if you want really, if you don't want to spend time, you need everything automated, which is not necessary for academic researcher. We have a lot of time in our life. But for industry people who wants to make things quick, they go for customized commercial solution because they don't want to do themselves anything. The software should do everything. But remember, softwares only produce results, and that is not science. Science is interpreting those results. So what software you use is finally your choice, and it does not matter. It's how you're interpreting those results that are important.
Thank you, Dr. Datta. I think it's been answered all the questions of Ananya Burman. I hope she will be happy with that. And so far, we don't have the question in the question answer box. And also, I can inform the participant that we have a group discussion session in the last day. So one session is for that. That there we can discuss about the any question you have during the whole 5-day FDP program. Our speakers will be there, so we will be able to answer your question over there as well. So if you currently don't have the pleasure to write the question in the question answer box.
Dr. Ghosh, there are
Yes.
some questions in the chat box as well. You might want to take a look.
Yes, sure, sir. Yeah, I think it's nice presentations. And then which books, sir? It's from Sandeep Joshi. I think the speaker has mentioned already. So
I just want to tell it that I have another session for the hands-on, and there
yes,
we'll get all the
yes,
links.
exactly, exactly. I am about to tell that the speaker will have another session as you have find the program schedule. So you can keep your queries safe for there, and then you can ask there in details also. One question from Papia Datta: for a faculty having PhD, do we have any scope to carry out further research in this field?
Yes, of course you can. Advantage of doing computational chemistry is that it's not like reactions which you have to monitor. So you can work at your sweet time and sweet space, and it does not need so much of the baby nurturing. That's the advantage, and you can work remotely. About you ask the specific positions of there. So IIT Bombay actually provides some summer programs where the faculties from other institutes where the facilities are less can spend some time here with us, so that they can learn what are the current trends and get access to the latest things what we have. So they, and I'm sure many other IITs have the same things. So it's always encourages people to carry the research, because if you want to do good science, then you have to know what are the current updates. So for teaching and research is not something very isolated. Teaching and research only do hands on hand, and most of the time a person who is good in teaching is very good in research, because the current philosophies are all same. How you can understand trends from there, and how you can actually explain it to people.
Okay, thank you. I think this will suffice the requirement of the questionnaire. And another question, maybe this is not many we can have, because we will be running out of time, because MAKAUT is currently organizing lots of FDP programs, so we have a constraint in time using the platform. Maybe just couple of questions we have currently, and if the speaker is generous enough to answer quickly. One is, the radiation the children are receiving these days due to the online classes are harmful. What is your opinion? This is the first one. And the second one is ORCA helpful to understand the conformation of synthetic peptide or oligomers with molecular weight less than 5,000?
Okay, I think the second question is more easier to answer, so I will answer that first. Yes,
Sure.
ORCA can do that. ORCA has QMMM codes, and we have some interfaces where it can do conformation search also, so it's very much possible. The first question is that, of course, there are damages happening due to the radiations which are prevailing these days, but don't get afraid. Our body is actually very smart. It's not dumb, so it has its mechanisms. And what we found in our all calculations up to now, and that's where everywhere, that actually the radiation damage is mostly mitigated by our body. And I can give you a very simple example. All of us are from this tropical country, India, and none of us are fair in that European sense. And why nature put us melanin in our skin? Because sun is very hot here. So if we go out in the sun, we don't get burns. We may a little bit tanned, but we don't get burned. Let a white man go in the sun. What will happen is that his skin will peel off. It's because of the radiation damage. The UV radiation will destroy his skin cells, and his skin will fall off. And that does not happen to us, because nature provided us with melanin. So nature is very smart. It tries to protect it as far as possible. But we should not take the smartness of nature for granted, and we should save for ourselves also.
Thank you, Dr. Datta, for answering all the questions so far we have. And I think we have to go to the closure of the session. But before we close the session, I think it's a little bit announcement for the participants. And because we will be using another platform, not the Zoom, the same platform. It will be using the Google Meet platform for the next session that will start from 3 p.m. today, the second session. And already the program schedule with the link, active link, has been shared with you, the participants, and all the registered participants. So you can log in through that link, and we will use Google Meet platform for this one. So I think Director Sir.
Dr. Ghosh, can I take just a moment?
Sure, sir. Sure.
Dr. Datta, let me thank you from the bottom of my heart, especially for your closing comment that software only produces results, and that is not science. Science is about interpreting them. Also, let me thank you for the elegant visual quality of your slides. I am not a specialist, so I'm not qualified to comment on the content, but the visual quality of your slides are excellent. They are clear. These are indicators to all of us of good teaching, how there has to be clarity, a clarity of thought, clarity of thinking manifests as clarity of writing, especially on PowerPoint. So thank you for that. And on a lighter note, that French philosopher you referred to. I could never pronounce his name as well until I ran into in my PhD days in Michigan, somebody from France, and he helped me learn the name, pronounce the name of that guy. I don't know if I still recall, but I would give it a try. It is called Auguste Comte. Auguste Comte. In Bengali, it would be Koy Chandrabindu Okar Khandatta. So, once again, thank you.
It's a jugglery
I
for the
appreciate
teeth and leaf. Yes.
Thank you for your kind words. I cannot still pronounce it, I guess.
So that guy actually, he has like the sociology, he coined that idea, positivist science. He was the one who basically was the promulgator of that philosophy. And the sociology, he kind of classified the very basic is physics and this and this, and eventually sociology being the more complex set of sciences. So anyway, that's my 2 cents worth.
So I think thank you, and thank you all for being present in the session. And we had a wonderful talk from Dr. Achinta Kumar Datta, who was generous enough to donate his time and share his uh, so far not that much work, and he will be sharing the work in the hands-on session, and I think that will be more interesting for our participant and more to know, and they have to wait for that thing. So I think we are good to close formally this session, and we will see at 3 p.m. all the participants with our panelists, and the Google Meet platform will meet, and you just follow the link that has been provided in the program schedule brochure. So I think, is anyone has something to say, or I don't know, formally I think we are good to close then. Okay, thank you everyone for joining this FDP program. Thank you.
Thank you all.
See you at 3 p.m. then.
Sir, the feedback
Yeah.
link has been given in the chat box.
Oh, okay. Just to tell then to the attendees that the feedback link has been given. You have to submit the feedback form, and also the link for tomorrow's registration has been given. This is using the Zoom platform, but I think for the second session of today's, as I said, just with the Google Meet platform, the link is also been shared with you. Just follow the Google Meet link for the second session that will start from 3 p.m. Thank you. Prem, I think this is in time, I guess, right?
Yes, sir.
Okay then. So,
Just we are closing the session, sir.
I think yes, we are good to close the session. So far, we have answered all the questions that has been put on the question answer box, and yes, we can close now. Yes.